Welcome to the chemistry video tutorial that will introduce the concept of chirality. This is a very important concept, especially in terms of biological activity, because what we're going to learn is most biologically active molecules have what we call a chiral carbon or chiral center. So let's get started and learn more about what in the world a chiral carbon is. Alrighty, now we've learned a lot about different types of isomers, right? So initially we started with learning about constitutional or structural isomers, right? And at this point in your mind you should have a definition of this term just popping into your brain. If not, just something to work towards, right? So we could have elements that or compounds that have the same chemical formula, but they are connected very differently. Right? So both of these compounds are C6H12, very different connections. All right? So now, that's same chemical formula, different structure. Stereoisomers are the most subtle. They have the same chemical formula and the same connections. It's the spatial arrangement that differs, okay? So different spatial arrangement. I'm running out of room. Okay, so this is a good brain yoga activity, all right? Visualizing things in 3 space, right? Oh, and so I tried to squeeze in the definition, and now we have plenty of room to write it here, right? Stereoisomers are compounds with the same chemical formula and atomic connections, right? But different spatial arrangement. Okay, and we've already learned quite a bit about those, right? We've learned with our long hydrocarbon chains, right, that we can have conformations. So we learned a little bit about Newman projections and that there can be a lot of rotation around the atoms, right? Rotation around single bonds. Okay. That creates one type of stereoisomer that we call a conformer. We've also learned about geometric isomers, right? So you should be, when you hear the word geometric isomer, you should be thinking about the trans or cis double bonds, or when we studied rings, right? That we could have the 2 substituents above the plane, or one above and one below, right? We use the wedges to show pointing out and the dashes going into the paper, all right? So here are all the isomers that we've already learned about. Now comes the new part, enantiomers. And this is where we have a chiral carbon, right? So what in the world is a chiral carbon? A chiral carbon is a tetrahedral carbon. All right, so we can put, right, so remember for tetrahedral, right, in the plane, and then there's the wedge coming out and the dash going back. Okay, so there's our tetrahedral carbon, right, but it is bonded to 4 different groups. All right, so we'll just say A, B, C, D, just to show that they're all different. All right, so now let's look at an example. Let's look at 2-butanol, all right? So if we look at 2-butanol, we will put, right, the OH group is there, and then this would be coming, the H would be coming back. So 2-butanol is a chiral carbon. There is the chiral center, because what? It has a methyl group, a hydroxyl group, a hydrogen, and an ethyl group. Right, methyl and ethyl. So if we draw this out, right, here's our chiral carbon with the star. Right, so if we wanted to draw this out, we would show, right there could be the hydrogen, and then, okay, this would be the OH, this would be our CH3, and then there is our ethyl group. All right, so we see 4 different groups. Sometimes when people are first learning about chirality, they're like, oh, but there's a carbon and there's a carbon. Aren't they the same? Well, we say no, because a methyl is not the same as an ethyl. Alrighty. So this molecule, we would say chiral. Now achiral, right? Remember when we have A, that means not chiral. So let's compare this with 2-propanol, right? So if we have 2-propanol here, we see that this is not going to be chiral because these are 2 methyl groups, right? So they're the same. So remember that it has to be 4 different groups. So when we draw out isopropanol, there's our methyl groups, right? So this is not chiral because these match. Okay, so that is the first thing we need to do, is look at the definition of what chirality is. Now that we know that, let's dig in a little deeper. So here is our next page. And so let's see here. Okay, right? So there's an interesting thing about chiral compounds. They will have a non-superimposable mirror image. Okay, so basically what that's telling us is that one chiral carbon, right, can create 2 stereoisomers, right, because we have a mirror image. So that's what this picture is showing us here. So here we're back with our 2-butanol, right? And here are the mirror images, and so I made some models of that to show you. So let me grab those models. Okay, here we go. Okay, so this model represents the compound on the right. If we look here I'm touching the carbon. That's chiral. Right, and then here's the OH and the hydrogen, and the methyl's poking out, and then there's the ethyl in the back. Okay, so here I'll hold the chiral carbon, and then here's the other chiral carbon, and let's see what there we go. Okay, so let's see if we can see. If I hold the 2 chiral carbons, so we can, here I'm touching the hydrogens, and then you see the OHs, and then the methyls, and then there's the ethyls, right? So we have mirror images, but if I try to overlap them, they will not superimpose, all right? This happens with our hands as well, okay? So if we have our hands, I'll do them this way, right? So if I try to overlap, right, there's our thumbs. Okay, so our hands are mirror images, but we cannot superimpose them, just like the molecules. So these are both 2-butanol, And this is where your model kits are going to come in really handy. This is an activity where you're going to want to make some models and convince yourself. All right? So chirality may seem like this really strange idea, non-superimposable mirror images, but they're part of our everyday life. All right? Chiral objects, they tend to come in pairs, just like we've seen here. And I wanted to, so we call this, right? So this would be the pair of enantiomers. Okay, so these are distinguished, but we're not going to worry about that for this class. We just need to know that there's two different compounds, right? So if we look at scissors, do scissors have a plane of symmetry, or no, right? So they are chiral, all right? So anybody that's left-handed that's ever tried to use a right-handed pair of scissors understands what I'm talking about. If we look at a baseball, though, this is another way. So you can think about non-superimposable mirror image, or we can think about having a plane of symmetry. Okay, so achirals have a plane of symmetry. So if we look at a baseball, we have a plane of symmetry, so it's achiral. The same thing with golf clubs. If there's any golfers out there, right, you can't use a left-handed golf club with a right-handed swing. It's also chiral. And I think most of us at some point in our life have put our foot into the wrong shoe, all right? So shoes and gloves are another example of chiral, right? So chiral things form a non-superimposable mirror image, and they do not have a plane of symmetry. So if there's a plane of symmetry, that's an easy way to spot that it's not chiral. Alrighty. So now that we've gotten a little more comfortable with the idea of chirality, let's go back into looking at compounds a little more closely. And let's see how you're doing here. Do your best to go in and find the chiral carbons, to put a little star. I'll let you know each compound has only one chiral carbon. All right, and don't be afraid to draw, right? So it's this OH group kind of makes it obvious, right? So there we have a propyl group. And here we have a butyl group. And then we have our hydroxyl group. And like, wait a minute, where's the other group? Remember, those hydrogens aren't shown. So we can see that we have 4 groups. There's our chiral carbon right there in the center. Okay, here's our chiral carbon here, right? A methyl, an ethyl, bromo, and of course hydrogen. This last one can be a little trickier. Our first instinct might be to go here, but we'd have 2 methyl groups. But if we keep looking right here, we would have this carbon branch. It'd be an isobutyl, a methyl, an ethyl, and of course the hydrogen. All right? So one of the skills you want to build after this video tutorial is being able to look at chemical compounds and identify the chiral carbon. It's also important to remember that we don't show the hydrogen often, so we have to remember to see the hydrogen. Okay, now let's bring in some nomenclature, tie this all together, draw the skeletal line structure for 3-ethyl, 4-methyl hexane, and star any chiral carbons. So 2, 3, 4, 5, 6. So I think I might have, oh dear. No, that's fine. Okay. There we go. So that's perfect. All right. So now let's see if we can find the chiral carbons. Our first instinct might be to look here, but notice we would have 2 ethyl groups. So this carbon is not chiral. Let's keep looking. Ooh, when we get here to this carbon, wow, okay, now we have this big, huge carbon chain here, right? 1, 2, 3, 4, 5, like big old 5 carbon chain coming off there. There's a methyl group. There's the ethyl group, and then of course our beloved hydrogen. So there is our chiral carbon. The carbon bonded to 4 distinct groups. Okay, now let's do a little more practice here. One of the following molecules is chiral, but the other 2 are not. Draw the skeletal line for each compound, circle the chiral compound, and star its chiral carbon. All right? So heptane, 2, 3, 4, 5, 6, 7. So there's our 7 carbon chain and a methyl group coming off of 2 or 3 or 4. Okay? So there we go. Now when we look here, well, there's matching methyl groups. So this is achiral. If we look here, oh, ethyl, methyl, butyl, and of course the hydrogen. So we have found our chiral molecule. But now let's double check. Why wouldn't this one be chiral? Because when we look right here, we see right there's 2 propyl groups coming off of this carbon. So it is also achiral. Okay. Now, because the spatial arrangement of the atoms is very important, it can be helpful to draw the molecules in a variety of ways. And so we've seen this before. Like for the rotation, we saw that we learned how to do Newman projections. Well, for chiral carbons, it can be helpful to use a Fischer projection. So we'll start with a achiral molecule, right, with the matching bromines. And we can see here, from now on, whenever we see a molecule drawn in this fashion, we will see that the verticals are representing dashes, and the horizontals are representing wedges poking out. All right, so for me, it helps to see like the horizontals, so the reaching out would be like a giant hug, right? So the horizontals poke out, right? It's like they're trying to hug us, right? The verticals are veering away, but the horizontals are trying to hug. So now we can, we have 3 ways to look. Here's our Fischer projection. Here is the Prospective Formula, and then we could show the definition of the Prospective Formula. So I think, what do I want to do here? Okay, so I want to show you this molecule really simply first before we go to the trickier one. Okay, so let's think about what we remember about, right? So now these are in the plane of the paper, and we see, right, that the bromine's poking out and going back, right? So this would be our Prospective Formula. I think I'll flip it this way to match the paper. Okay, so there we go. So these are in the, see how they're in the plane of my hand. The hydrogens and the bromines poking out and going back. And so then basically the Fischer projection rotated it like this. Okay, so the horizontals are the hugs and the verticals are going back. Now let's try one that's a little trickier. Let's see. Okay. Here we are. All right, so now we'll go to an actually chiral molecule. Okay, so here we can recognize that we have a chiral center because we see that we have a hydrogen atom, a bromine atom, a methyl group, and a hydroxyl group. All right? So if we take this model and I put it, perfect. Okay, so here we go. Now this is, I'm holding the chiral carbon, so here's the hydrogen and the hydrogen, and then the methyl group, and oops, the methyl group there. Okay, so the OH is a wedge, it's poking out, and the bromine, orange, probably not the best color, but oh well, okay, it's going back. Alrighty, so what we want to do to make this into a Fischer is, this one's already poking out, let's just roll it around. Alright, when we roll it around, here's our Fischer, right? So the methyl group is still at the top, and the hydrogen group is still at the bottom. There's our hydrogen, there's our methyl. The OH is now on the left, and then there's the bromine, right? So let's try that one more time. So the hydrogen and the methyl and the chiral carbon are all in the same plane of the paper. The OH is poking out, the bromine is going back. To make it into a Fischer projection, we just rotate like this, and now we see that the methyl and the chiral carbon and the hydrogen, methyl, chiral, hydrogen, OH on the left, bromine on the right, right? So you want to get good at switching back and forth between a Fischer and a Prospective formula, and vice versa. So here we have the Fischer projection. Let's practice drawing the Prospective formula. So I'll give you a hint, right? Put them in the same plane, right? There's our CH2, CH3, and there's our hydrogen. Okay? So remember, these are the wedges poking out. Alrighty. So what we want to do is, oh, yeah. Okay. Let's see here. So I'll give you guys a chance to work on it, and I'll get the model ready, and then we'll compare answers. So go ahead and do your best to draw the Prospective formula for this compound, and then we'll work on it together in just a moment. Okay. Alrighty. Here we go. Right, so I bunched things together to make it a little easier to see. All right, there's our hydrogen at the bottom. There's our chiral carbon. There's our ethyl group. We have a bromine on the left and a methyl on the right. Okay, so we just rotate into the plane. The hydrogen, the chiral carbon, and the ethyl are all in the same plane. So the bromine, it's still poking out. It gets the wedge. And the methyl group is going back into the paper. All right? So this is a skill that you want to practice, because practice makes perfect. And it will help you to be able to see the relationship. Okay, why is this so important? Well, let's look here. It's important for a couple reasons. One is that enantiomers, they share many properties. They have the same boiling point, the same melting point, the same density, the same refractive index. That's how they bend light, and how they dissolve in substances' solubility. So if everything's the same, why do we make such a big deal out of them? Well, they interact differently with polarized light and other chiral compounds. And that's a big deal because this is about our biochemistry. Because most of the interesting molecules in our biochemistry have these chiral carbons. So chiral carbons only want to interact and hang out with other chiral molecules. All right. So let's look very briefly at this idea of polarized light. Enantiomers, right? Because if we have a chiral carbon, we get a pair of enantiomers, and they are going to rotate light in equal but opposite directions, all right? And so sometimes enantiomers, right, they're called optical isomers. So because of this interaction that they have with plain polarized light. So mostly this is in here for vocabulary, all right? And it's just good to learn about light. It's important. Alrighty. So polarized light is where we have a filter, and it causes all of the light waves to vibrate within the same plane. And so then what happens then is if we have one pure enantiomer, right? So we have the plain polarized light. When the light interacts with the sample, the chiral compound rotates the light. So I'm going to show you an example of this with some filters. All right, so here's a flashlight, and then I'm going to put this filter in front of it, and so you can see the light coming through. Okay, so now you are looking at plain polarized light through the filter. All right, so now if I take it, so if this second filter is going to act like the enantiomer, and it's going to rotate the light until voila. Notice how the light goes away, because now they're at 90 degrees to each other, right? And then if I rotate back, the light appears, okay? So this filter is showing you what an enantiomer would do, right, about this rotating type of thing back. Alrighty. Okay, so not a huge emphasis in the course, but something in it, we're going to build on that. So because the pair of enantiomers are distinguished by how they rotate polarized light, they're either given a D or a plus if they rotate light clockwise, and an L or a minus for counterclockwise. So as you're doing your molecular portfolios, your drug name may begin with a D or a plus or a L or a minus. And if you're wondering what that part of the name is all about, it's telling you that your drug is optically active, that it's chiral, and it's giving information about which enantiomer is actually present in the drug. And so let's keep going on that, because the main point of chirality is that biologically, enantiomers react very differently. Like, let's look at epinephrine, also known as adrenaline. And if we look at it closely, your eyes can probably spot the chiral carbon pretty quickly. It's right here. And so within our body, we want the minus version. So here's an enzyme active site. And when we have the minus version of epinephrine, it fits perfectly into the active site, and we get biochemistry. If, however, oops, I gave you the sneak peek of my notes. Okay, right? So here is our minus. So we see the minus enantiomer fits perfectly into the active site of the enzyme, and so we get a reaction. Okay, if we have the plus enantiomer though, now we see that the groups do not fit properly into the active site of the enzyme, and so there's no reaction. All right, so this idea of chiral carbons is very important in our biochemistry. Here's just a couple more examples. Vitamin C, ascorbic acid. Here's our chiral carbon. You can usually spot them because you'll see the wedges and the dashes, right? So this form of vitamin C is a nutrient. This form of vitamin C has no biological function. So chiral carbons are very important to our health. And here's an example, right? Here's thalidomide in the 60s, I think the late 50s, the early 60s. Here's the chiral carbon here. Let's see, there it is right there. There's the chiral carbon. And this helps relieve nausea. All right, so a lot of women that were pregnant, mostly in Europe, they started taking this drug. But it turns out that the other form is a teratogen. And so the babies were born with the flipper hands and feet from the effects of the other enantiomer. So being aware of chiral carbons is important, and knowing that some forms support our health and some cause disabilities or birth defects or other unpleasant things. So that wraps up our introduction to chirality. Please take some time now to work with your models, build some chiral molecules, build the mirror images, and really get comfortable with this idea, because we'll be building on it throughout the rest of the course.